Okay, we have 1 minute. Just wait for people to show up. Okay, good afternoon, Gaetan. Hello, it's Jamie here. Yeah, here, I'll just step into the camera there. Now you can see me. Yeah, here I am. And, okay. Sorry. Okay, I think we're ready to get started again. So we have Gaetan Borot from Berlin, who's going to give us his second lecture of his mini course, and today's title is Finger Dyson Equations and Loop Equations. Welcome.
Thank you. So today we talked about various Hermitian matrix models yesterday. And so let's recall the type of measure we were considering on Hermitian matrices. There was some normalization constant. There was a Lebesgue measure on the independent entries of the matrix. And then we put exponential of, so before I had the Gaussian term and then a higher order term. Today I'm just going to absorb everything into the function T01. And we saw that we can also consider multi-trace matrix models. So that was the first, it involves linear combination of product of two traces of powers, and there can be higher order terms. I will try to focus just on these two first terms and indicate what changes at the end if you add the others. So the first thing which I want to mention is that you can also, instead of working with the matrix entries, you can diagonalize the matrix. So up to a unitary transformation, you can write it as a diagonal matrix with real entries. And since here everything only depends on the spectral invariance of M, that's not going to depend on U, it's only going to depend on the lambdas. So there's a Jacobian when you do this change of variable from M to U and lambdas. And so you will get the Haar measure, a certain constant depending on N. And here the Vandermonde of the eigenvalues squared. And this square is a sign of Hermitian matrices. You can then, so the measure would look like, so 1 over Z, the U constant, this Vandermonde to the square. So the Lebesgue measure on the lambda i's. The Vandermonde squared. And well, here in the exponential, you have N and the sum over I of T01 lambda I. The next term is the sum over I and J of T02 lambda I lambda J. And so on. You would have function of many variables of a K tuple of eigenvalues. So this is a bit more explicit to work with. And I'm very soon going to, anyway, we can integrate out this unitary matrix. So we really left on the measure on N real variables, the lambdas. If in general we have F, which is some analytic function, near the real axis. So in the complex plane, in the neighborhood of the real axis. And you want to compute the expectation value of the sum of the f of lambda I. Just by the way this W1, this correlation function was defined. So this is the sum over I of 1 over x minus lambda I in expectation value. You can use Cauchy residue formula to write it in the following way using W1. So dxi over 2I pi, where the contour should surround, so all the possible eigenvalues, so should surround the real axis. So if you don't like this, you can just say you truncate your model to have eigenvalues bounded, and then you take a circle around that. And indeed, if you compute this integral, you're just going to see, so you can take this expectation value out of this contour integral. And then you see xi divided by 1x minus lambda I. So it's going to, so you substitute x to be equal to xi. So you're going to have a simple pole at each lambda I. And then it just makes, the residue evaluates the function f at lambda I. So it's really doing this expectation value here. So we're going to use this to represent the expectation value of any function of the lambda i's, to express that in terms of contour integrals of the w's. So one very important tool to study matrix models is the so-called Trinidadian equations. And it expresses the fact that the partition function is z, which is the integral, so up to, so I integrate out the unitary matrix. So I may have another constant here. So is this integral over the lambda I of all these measure. And an integral is invariant under change of variables. Equivalently, it's invariant under, you have integration by part. So both properties are intimately related. And so we want to express the Trinidadian equation as any sort of relation between observable that you obtain using either integration by part or invariance of the integral under change of variables. We're going to assume that here this goes fast enough towards minus infinity so that the measure goes to 0 when the lambda i's goes to infinity. So normally when you do integration by part, you have boundary terms. And because of this property, if you assume this is vanishing at infinity, you can ignore, there's not going to be any boundary terms. So one way to get effectively all the equation that we need is to look at an infinitesimal change of variable of this form. So you may wonder that x is complex. So you don't like this because it's not really an allowed change of variable. We're integrating here over Rn. But in fact, this is just a convenient way to collect all these change of variables here with some power k. I can do that for each k. And then I can sum over k, divide by x to the k plus 1, and then I will exactly obtain formally this. So one can justify properly what I'm going to write. And so let's see what we obtain. So if you express the fact that z is invariant under, under this change of variable. So first, there's going to be a variation coming from the Lebesgue measure. And we're going to express the integral is invariant at first order in epsilon. So it means that the product of d lambda I at first order is going to become 1 plus epsilon, here the sum of 1 over x minus lambda I squared. And then there are terms coming from the van der Waals squared and coming from the variation of the lambda I in the t's. So at the end, you're going to obtain many terms. And they're going, so what I can, okay, maybe I can write something like that. So this product here becomes itself, and here I have the log derivative. So the sum of all I smaller than j, 1 over x minus lambda I minus 1 over x minus lambda j, and 1 over lambda I minus lambda j, plus higher order. And then I have these terms. And again, so we do that with the log derivative. And so this times 1 plus, so at first order, I'm going to have n sum over I t01 prime lambda I over x minus lambda I, and the term coming from variation of the t02. And since I'm summing over all I and j, I can assume that c02 is symmetric. So normally I have variation of the lambda I and of the lambda j, but that this is symmetric, I can just do variation of the lambda I, and then it will cancel the factor of 2. So I sum over ij, d lambda I t02 lambda I lambda j over x minus lambda I, and then higher order terms. So when I integrate, I should get something which doesn't depend on epsilon. And so if we collect the terms at first order in epsilon, we get, so recognize that all these factors, it reconstruct the measure that we have. And so what we see is an expectation value. So let me simplify a bit this one. I can put in the same denominator. I will have lambda I minus lambda j canceling the denominator. So I have this. And I forgot the factor of 2. And here I have these terms. So n sum over I t01 prime lambda I, x minus lambda I, and sum over ij t d lambda I t02 lambda I lambda j x minus lambda I. And the expectation value of all of this is 0. These terms recombine well together. If I say that, well, this is symmetric in I and j, so I can, instead of summing over I smaller than j, I can sum over I different from j and then remove the factor of 2. But then at I equal j, I can pick up this term. So all together, these two first sums become just the sum over I and j, 1 over x minus lambda I, x minus lambda j. And then I have the rest. Good. And now we would like to express this in terms of correlation functions. So here we recognize exactly what we would have in the 2-point correlation function, except that I didn't take the cumulant here. It's really the expectation value. So I can say that this is I should write the details. So this is the cumulant plus the term which we removed in the cumulant was exactly the product of the expectation values. And then I still have these terms here. So this part we recognize directly that it's W2XX. And here's W1X squared. And now I have to treat the rest. So for the rest, we use what I mentioned before that, I mean, these T01, so we're always going to assume our T's are analytic in a big enough domain. So it looks like an expectation value of the sum over I of f of lambda I. So that I can represent using a contour integral. So it's dxi over 2I pi, T01 prime xi. So the rule of the game is that we replace lambda I by a variable xi on which we do the contour integral. And so remains x minus xi in a denominator. And for the next term, we have lambda I and lambda j. And this is something which we assume, so all the T's are going to be analytic in a big enough domain. So this, we just need the many variables generalization of this formula. If I had sum over I and j of f of lambda I lambda j, I would express everything in terms of 2-point functions. So using the same trick, because we need the W to is defined in terms of cumulants and not the moments, what you would find is a double contour integral, dxi1, dxi2. So I replace lambda I by a variable xi1, lambda j by a variable xi2, on which I'm integrating. And then I see x minus xi1. And that is multiplied by W2 xi1 xi2 plus W1 xi1 W2 xi2.
Gaetan, one question. Can you say something about this contour integral? Where does the contour goes? Is it around 0 or no, around
So
infinity?
this is around the real axis.
Yeah.
And this is why I'm saying that we want to ignore everything that happens at infinity. So if you prefer, if you don't, normally you would say you have a contour which is just above, I mean, you have actually a path which is just above the real axis and then just below, and you close it at infinity. If your eigenvalues are allowed to go at infinity, you have problems. What I'm saying is that effectively you don't have problems providing that you chose your T so that this measure goes to 0 quick enough at infinity. So for that reason, it's up to exponentially small corrections in n. You can think that all the eigenvalues are in a segment on the real line. And then this contour is just going to be a circle around this segment.
Okay, yeah, thank you.
I had a question too, Gaetan.
Yes?
So I thought the x minus zeta was already included in the W1 of zeta. Didn't you already put that in the denominator? Or are you putting one? Yeah, so
if
that
I look
already
at
had
this,
the denominator thing in the denominator, right?
So W1 is defined as this resolvent. So it has the 1 over x minus lambda I, yes.
Right.
But if I look at this formula, I just see exponential expectation value of sum of I of f of lambda I.
Yeah.
And that is a contour integral involving the W1. And the f is in front. So I just take my f. In this case, so I see what is f. F as a function of lambda I, it's T01 prime lambda I divided by x minus lambda I.
Oh, okay, I see. So there's two things in the denominator. Okay. Okay,
Yes.
great. Thanks.
So this is the first Trinidadian equation. And it's not an equation that we can directly solve. For example, I mean, you would like, for example, the first question is, can you compute W1? It's already an equation involving W1 and W2. So you would need to find an equation to determine W2. So if you want to go higher, there's other Schrödinger Dyson equation you can derive. Because here I just express the fact that this partition function has an integral, it's invariant and a change of variables. But the correlation function themselves, their expectation value, so it's also an integral. And you can express that this is invariant and a change of variables. And you're going to obtain new equations which involve the higher order correlators. An effective way, so again, it's something you can justify, but it takes more time. So I just give you the quick way to get the correct result, is to say that, well, this equation is valid for any t's, so you can start to vary the t's. So you can define an operator delta xi, which is formally d over ds at s equals 0 when you change the t01 to be t01 lambda I minus s over n, sorry, plus s over n 1 over xi minus, so I don't like the lambda I, so I just put lambda. So if you formally do this change.
Sorry for interrupting you again. The W2 does not have a prefactor 1 over n squared in your...
Not in the way I defined them.
Okay, not in the way you defined it. Okay, yeah.
So indeed, then when you do large analysis is going to be of a certain order.
Okay, yeah, thank you.
So if you formally do this, I mean, all these W's here do depend on T01 because that comes up in the measure and that's an cumulant expectation value. So if you look at the way this is defined, in fact, delta xi applied to Wn, to W, I call that y, and to Wn x1 xn is in fact going to be Wn plus 1 x1 xn and y. Because in the measure, you're just adding these things with a sum over, so some of the different eigenvalues, lambda. And so when you do this d over ds, it's exactly come from the way, it's exactly the same thing as the way the cumulant were defined. So you just get a higher order cumulant applying this. So let's apply delta x1, I mean, many times this operator on the first Schrödinger Dyson equation. So I act on W2xx. So here we're going to get Wn plus 2 xx and then x1 xn. On the W1 squared, so it's Leibniz rule. You have to say to which of the two factors you're going to apply which deltas. So you split the variables corresponding to this derivation in two parts. The first part is going to act on the first W1, so it's going to create a W1 xj, so there's cardinality of j more variables here. And then you have the next one. And then we have to look at the other term. So here, there's two things that depend on T01. There's T01 prime itself, and there's W1. So when you have n of these derivations, you can let act one of them on the T01 prime. Then you're going to see the derivative with respect to lambda of this term. And all the other derivations have to act on the W1. So you're going to get the sum over I from 1 to little n. And the contour integral. So the derivative with respect to lambda of this T01, this is 1 over x minus, and then you replace lambda by xi, so it's x minus xi squared. And then you would have the wn plus 1 xi and the x1, where you don't take the xi here, divided by x minus xi. And there's a 1 over n here, so it cancels this step. So that's one term. And then you have the other term where you apply all your derivations on the w1. So this is t01 prime psi wn plus. So how many x's did I have here? I just had n. Here I started with 1 and I apply n times, so I increase by n, so I get wn plus 1. So we get this. And then when I go to the next term, here, this t02, it's independent of t01, so you don't have to act on, to use the derivations on it. You just have to use the derivations on these w2 and w11, and that we already know what it gives. So you would obtain this. So d xi1 t02 xi1 xi2 x minus xi1, and then wn plus 2 xi1 xi2 x1 xn plus the sum of these two w's. Good, so it looks complicated. We're going to try to tame that a little, at least give the results of how it is tamed. So it's the nth Trinidadian equation. And now it involves w, so it involves w n plus 2, but also wn plus 1, wn up to w1. In this factor, you're going to have some w1 where all the j prime is an empty set, for example. So these are exact equations. They're true for finite n. And they give relation between correlators, but not really a way to compute the correlators.
Sorry, just one question here.
Yes.
I mean, did you say that these equations can also be derived using integration by parts?
Yes.
Okay, so that would be a different proof, right?
Yes. Well, so, you know, I guess from calculus course that the way integration by part comes, it's more or less, you can prove it by change of variables. Or these two things are really an infinitesimal version of the other.
That's basically, that boils down to that. But I mean, this.
It just boils down to this.
Yeah.
So you can write what is here as a total derivative.
Right. Yeah. Yeah.
I mean, the integral, because there's a measure. So in order to go further with this, one has to study the large n limit. So the first thing is that under weak assumptions, this W1, so it's expected value of a trace. A trace has order n terms, so you expect that when you divide by n, this has a limit. So the limit exists. And then if the limit exists, In fact, one can prove a bit more here using concentration of measure. So it's a whole topic in itself, which I'm not going to explain here, but you can also see that this W N, so in particular, maybe I just look at W2 for the moment. It's negligible compared to N squared. So normally W2 is this cumulant of the product of two traces. So each trace is of order N. So you may expect that to be at worst order N squared. And the concentration of measure guarantees you that it's actually slightly lower order at least.
So Gaetan, to do that, it's Jamie here. Do you
Yeah.
have to know something about Poincare inequalities and largest eigenvalues and things like that to make that?
No, it's much weaker than that because you only need macroscopic behavior of eigenvalues.
I see. Okay.
If I didn't have this T02,
yeah.
Then, so you see here the logarithmic energy, and this is a strictly convex functional. Therefore, in terms of on the space of probability measures,
yes,
on R, which you see as your distribution of eigenvalues, this is going to have a unique maximum.
Okay.
And moreover, the empirical measure of the eigenvalues, so this 1 over n sum over I, Dirac mass at lambda I.
Mm-hmm.
Under rather weak assumption, you can prove it converges almost surely in expectation to a deterministic measure. So that's a random measure.
Mm-hmm.
And concentration of measure, it's really weak. It's using the strict convexity of this energy functional.
I see. Okay.
And in fact, it gets you automatically an n log n here.
Okay.
So you have even better than that, you have n log n.
Okay, because I recently looked at this for just W2, and we used a Poincare inequality and estimates on the largest eigenvalue to actually prove that something converged. But okay.
So with this, you cannot prove the W2 converge. You just prove some a priori upper bounds.
Oh, I see. Okay. Okay.
The point is that with Trinidadian equations, you can improve these bounds to the optimal one and actually prove things converge. There's a general strategy to do that.
Okay, thank you.
So for the moment, let's just take that as input and see what happens in the Trinidadian equations. So we look at the first one, we see W2, and we see W1 squared. So all of that, you see here an N, a W1. So the largest term are going to be of order N squared. But since W2 is negligible compared to N squared, W2 is going to disappear in the large N limit. So you're going to get at the leading order, is N squared of the first Trinidadian equation. You would get W01, so this limit squared. You would get this contour integral of the T01 prime psi W01 psi x minus psi, and the double integral of the xi1, the xi2, 2i pi squared. And what did we have? We had dxi1 T02. Divided by x minus xi1. And here there was a W2, but again, it's negligible compared to the n squared scale. So you get W01, W xi1, W01, xi2. It still looks complicated, so it's a nonlinear and integral equation, but only for W01. So it's better. We just have one unknown to solve for. So to arrange it a bit better, we're going to write it like this. So if here I was not putting, oops. Let me see, what do I want to do? Yes, so if I'm putting T01 prime X instead of this, then I have this contour integral. The contour is around the real axis. And then because W, if you took this T01, so if you replace that by a T01 prime X, of course, then you have a contour term. But the integral of xi then becomes, you can move the contour integral towards infinity because W01 is analytic in the complex plane minus the real line by its definition. And then you're going just to pick a residue at xi equal x, and it comes with a minus sign because you're increasing your contour. So you're going to see just W01x. So there's a term like this. But then, of course, I had to add the contour term. So what do I see here? X minus xi, W01 xi. So before going further, let's explain why we wrote it like this. Imagine that T01 was a polynomial. Then this quantity here, this ratio, it's also a polynomial in X and in Xi. Therefore, it's whatever it is, this thing is going to be a polynomial. The full contour integral is going to be a certain polynomial, which I don't know, but I only know, I at least know it's a polynomial. If this is not the case, I say that I want to assume that the T's are analytic near R. And the thing that you can say, so I'm just going to call it P, at least it's analytic when X approaches R. Which was not true here, because X here must be outside the contour for the way I define things. So if you want to let X approach to the real axis, you have to put it inside the contour. So you may have, this thing may have a discontinuity on the real axis. But it's not the case anymore here. That's now holomorphic near R. So that's going to help us. And we're going to treat in a similar way the other terms. So we're going now to replace, so we want to get rid of this 1 over X minus Xi1 that may create something which is not continuous or not holomorphic when X approaches the real axis. So I want to replace the numerator. In the numerator, I want to replace Xi1 by X. And if I have that, then, so I have dx T02 X Xi2. And then I can do the integral, the contour integral in Xi1, I will get the W01. So we're going to see the contour integral in Xi2 that remains. Here's some dx T02 X Xi2, W01 Xi2 times W01 X. But then I lost a term, and I claim that this term P tilde, so maybe I call that P01, P02, whatever it is, I know it's going to be analytic when X approaches R. So with this manipulation, we can rewrite our equation as a quadratic equation, W01x squared.
Is P02 also polynomial?
If T02 was a polynomial, it's going to be a polynomial for the same reason I had before.
Okay.
If T02 is only analytic, you only know it's analytic across R. So here we see there's a W01x, which has a prefactor. Let's call it T tilde 01 prime x. And then there's some P. So P01 plus P02, I just write it P. And that equal to 0. And what is T01x? Tilde, it is T01x plus this contour integral here. It involves W01, which I don't know, so it could be a complicated function. But by our assumption, it is analytic near R. So seen like this, it's a quadratic equation after all, so I could solve it. Here I didn't have any more derivative. Plus a half square root of T tilde 01 prime x squared minus 4p of x. Okay. So I cannot say that I have computed W01 because I still don't know this p, and even in T tilde 01, there's a W01 involved. But I know what's inside the square root is analytic. Therefore, it's going to have, on the real axis, therefore it's going to have isolated zeros. So I learned that this W01 of x is going to be of the form m of x and a square root here that may have several factors. So that correspond to the simple zeros, and the other one correspond to the even order zero, which I could factorize. If you agreed with me from the start that we make assumptions so that nothing happens at infinity, the eigenvalues prefer to stay in a compact region. So in a compact region, that's going to have finitely many zeros. So here you have a finite product. Good. So W01 should have a discontinuity where the eigenvalues live. And indeed, the square root has a discontinuity. So from this, you actually, yes?
All the AIs are different?
Here, yeah, I can always assume they're different because as soon as I have 2 or 3 or 4, I just take the biggest even number which I can take of them, and I put that out of the square root.
Okay. But what have, yeah, okay, yeah, thank you. Sorry.
Sorry, Gaetan, one more question here.
Yes.
So is a sort of one-cut lemma or multi-cut lemma something?
I'm exactly going to come to this.
Oh, okay, yeah, thank you, yeah.
So another thing one can prove is that, in fact, the number of simple zeros should be even. And then you can always order this. And I'm only going to care about the real zeros because I want to look at that only in the vicinity of the real axis. So from this, we can deduce that the eigenvalue condensate on the union of these segments. So of course, when you want to prove that, I mean, there are assumptions. I was not at all precise here. I just wanted to show you the mechanism, how you get some information about W01 using a Dyson equation. If you make some implicit assumptions. And so it means that we're in the H-cut level, the H-cut regime. Okay. So moreover, if M remains positive, so it doesn't vanish on this segment, then we say that we are in the off-critical regime. Which roughly means that if you vary slightly T01, in fact, all these things are, you can prove they're continuous in the coefficients of T0, T01. Therefore, this property that having you just have exactly 2H simple zero is not going to change. So off-critical regime means you stay in the H-cut regime even when you perturb with the T01. And now, so it's a theorem that in the one-cut regime, so you have only one segment plus off-critical plus a few other technical assumptions, but these are the most important one morally. It turns out that the WNs have an asymptotic expansion of the following form. To all orders. And here I'm really meaning, so I made a transition here, I'm talking about conversion matrix model where you do have a true probability measure, and this is an asymptotic expansion. And in this case, the WGNs are also, have power series expansion in the T's of yesterday. So the coefficient of T01, one of T02, etc. And the corresponding formal power series are the generating series of maps or stuffed maps. So they are the correlators of the formal matrix model. So that's a situation in which the formal matrix model and the conversion matrix model somehow agree. But if you're in a multi-cut regime and you're still off critical, plus other assumptions, then this is wrong. There are oscillatory terms. So these type of results for the one-cut regime first appeared in the work of Albeverio, Pastur, and Sherbina. About 20 years ago. And then it was systematized and generalized in a series of work with Guillaumet, also with Kozlowski. So with Kozlowski, that's the one including T02 and actually also all the THK, which I didn't talk about here. And here we can also do the multi-curve regime, so one can be much more precise. What does the asymptotic expansion look like? So one can describe to all orders what it is. And so here it's a combination of techniques from large deviations and from analysis of the Trinidadian equations.
Gaetan, can you
Yes?
say something about these oscillatory terms, how they look like or where they come from or what? Yeah.
So they come from the fact that when you have several, so physically, if your eigenvalues want to be in several segments, you may take one eigenvalue here and send it there. That's not going to cost a lot of energy.
Like a tunnel effect in quantum mechanics?
So exactly, there's a tunneling. And this tunneling, however, if you take a particle here and you move it there, of course, the measure, the potential and so on is going to look completely different. Or if you do expectation value of, I don't know, trace of M, at subleading orders, you're going to see some difference. And having this tunneling is going to make you appear some pseudo-periodic functions of N.
So if these two segments are separated with a large distance, the tunneling will decrease? So then
Sorry,
if they are separated with a large distance, so there's a big gap between two segments, would it have?
Then this oscillation would be indeed smaller.
So you're nearly have this asymptotic N expansion.
Exactly.
Okay.
However, you should be very careful if you have two parameters, the N parameter that you want to send to infinity, and the parameter by which you vary the distance between two segments, which is a coefficient. Let's say it's related to how you deform your T01, for example. And you should be careful whether these limits commute or not. Okay. And that can be a subtle point. So this is, I would say, for a summary of what is known on the probabilistic part that guarantees that such expansions exist. And once you know they exist, in fact, the coefficients are computed by the topological recursion. Using the large N data, so it's the spectral curve, which is y equal W01 of x. W01, we saw it's in C, it's an analytic function in C minus the segment. But because you have a square root and this M is analytic, you can try to analytically continue it. So the spectral curve is the Riemann surface on which W01 admits analytic continuation, the maximal one. And in topological recursion, you also need, imagine it appeared in some lecture, the so-called fundamental bidifferential of the second kind. And this is given by W02 plus 1 over x1 minus x2 squared dx1 dx2. So in this particular setting, W2, the first term is exactly n to the 0. So W02 is just the limit when n goes to infinity of W2. It turns out to have also analytic continuation on the same Riemann surface. On the same spectral curve. And that's what you have to take for, so the omega 02 in topological recursion. And once you know there exists an expansion, I would say this is purely playing with Trinidadian equation, analytic continuation, and this is pure algebra. So this part is so due to NR when there's no T02. It's due to a joint paper with NR and Orentin. When there is T02, and it's due to in a paper of myself, I think in 16 or 15, I don't remember, in fact. Maybe it was 15. When you have all the THK. But in that case, you need what is called blobbed topological recursion.
And can I ask again something? So
Yes.
this oscillatory terms, can you compute them also with topological
Yes.
recursion? This is resurgence, or is it related?
No, it's weaker than resurgence, because you're still doing asymptotic expansion. You're not trying to reconstruct the full thing as a function of n. And so the multi-cut case was predicted. So there's a formula. Sometimes it is called non-perturbative topological recursion, but it shouldn't be confused with resurgence. We just need a name, and we haven't found a better one so far. And this was predicted by Enar and David, I think around 0.6, if I remember. And then it was further studied by Enar and Marino. So again, just purely algebraic table, and then it was proved that this does give the asymptotics in these papers here. And so here it mixes the topological recursion with some theta function attached to the spectral curve. Okay. So I think remains 5 minutes. Is that correct?
Yeah, maybe that's more, yeah. We've got somebody starting in a couple of minutes, but yeah, go on for a few more minutes and then we can continue on tomorrow with the rest of it.
So given the time, I'm not going really to say how, so first, the thing I want to stress is that all these things is proved by heavy analysis, relying heavily of the Trinidadian equations. And instead of showing you bits of this analysis, I want to stress what is the important feature that makes that possible in the Trinidadian equations. So that was two larger limits, so all order expansion. So instead of writing the details of the Trinidadian equation, I'm just going to say to write the terms it involved. There was a W1 squared, there was a W2 for the first Trinidadian equation, and some W1 term. So that was here, and I'm going to also remember which factors of n were here. So in front of this one, I had an n. And of course, it's not just those, it's those with operators acting on them. For example, these contour integrals against T01, T02, and so on. So we saw that the n squared order term was only involving, well, W01 squared, and then W01. And so that was a nonlinear equation for W01. And if I want to, imagine you want to go to the next order. So the next order, because of the special structure here of the asymptotic expansion, which is also a feature that you can prove from the Trinidadian equation, you see that the power of n jumps by 2 each time. So the next term is not of order n, it's of order n to the 0. And that's a feature of Hermitian matrix models. So in that case, here you would see at this order some W02, some W11, W01, and some W11 in certain combinations. So we have we'd already know W01 from the previous step, and we have W11 and W02, which was actually W02 of, yeah. Okay, so how do we deal with W02? Let's have a look at the second Trinidadian equation. So this one, it was here. And I'm setting n equal 1. Actually, that's n plus 1, I think, in the way I label things. So if I look at the second Trinidadian equation, I'm going to get W3, W1, W2. Here's some W1. And more or less that's all. So we're going to see some W3, W1, W2, some n W2, some term involving W1. Was there an n here? So that's n W2 from here. You have W1 without an n. And that was all. So the leading order here is of order n. I have to take the leading order here and the leading order here, and the leading order W2 is order 1, so that indeed makes this n. So it's going to involve some W2, and actually some W2, W1, so W2, W01, some W2, 02, and some W01. And the great thing here is that we already know W01, so we get a linear equation for W02, which is the thing we didn't know in the previous equation. And so, okay, so now there's a certain linear operator acting on this W2. This linear operator, its expression depends on W01, but it's a certain linear operator that we already know because we already know W01. And we just have to invert the linear operator to be able to solve this equation. If we do this, then we can come back to this equation and say, well, now we know what is W02, but we're looking for W11. And again, this is a linear equation for W11. And in fact, it's the same linear operator, which is acting here on W02 and on W11. So it's a general feature of Trinidadian equation, which is the reason why we can actually conduct this large analysis, that although the equation for W01 is nonlinear, all the other equations form a triangular system. Of the form a certain linear operator acting on WGN equal to something which, so there was this piece of thing that we don't know, but we know they're analytic. So it's come from these P terms, plus something that involves only Wj prime n prime with 2g prime minus 2 plus n prime smaller than 2g minus 2 plus n. And so the work is to invert K. If you can do that, you can solve everything. And the reason why in the one-cut setting it does work is that K is invertible. So this is a moral theorem. I was not at all precise about assumptions, but it is a theorem with precise assumption that can be written but takes more time. So essentially it's because it's off critical. Plus 1 cut. Okay. So I think what I will do tomorrow, I will write the form that you can deduce from this, which is called the loop equations. For WGNs. And I will try to explain how topological recursion naturally comes up when you want to solve those loop equations. Sorry for going over time.
Thanks.
Thanks, yeah. So we've had a few questions. Maybe there's just one short question before we go on to the next speaker. And for Gaetan, there's nobody from the Zoom audience has had a chance yet to say anything. I see nothing in the chat. Okay. Nobody sees. Okay, so let's think Gaetan again. Yeah, we'll start the next talk in a couple of minutes just to let the Carlos get set up. Yeah, thanks, Gaetan. Yeah.
Thank you.
Yeah, Carlos needs to be able to share the screen. Yeah. Okay, I'm just going to go to the bathroom while we're